Electrochemistry combines chemistry with electricity. Right beside me you see an Erlenmeyer flask with a chemical. And the reaction is not started as usual, the second reactant, that is the second chemical or heat, but with green electricity. In the future, we at Evonik want to start a large part of our reactions with green electricity. Electrochemistry can in future make a major contribution to the green transformation of the chemical industry. One example is the water electrolysis as shown in the picture beside me. This process uses green electricity to extract the green energy source hydrogen from water. Electrochemistry is a sustainable and efficient technology. It reduces the use of chemicals because no second reactant is needed anymore as it uses green electricity. To some extent, you can even eliminate entire process steps when using electrochemistry. Electrochemistry makes it possible to recover raw materials. As a result, it is a technology for the recycling economy, or rather circular economy. When we use green electricity in electrochemistry, we can reduce Evonik's CO2 footprint even more. This is why electrochemistry is a next-generation technology for us at Evonik. Accordingly, electrochemistry is important for us when it comes to the transformation of the chemical industry. In the next 5 years, Evonik will spend a double-digit million amount to further expand our technology platform of electrochemical processes and products. About 20 employees are doing research in this field of activity at Hanau and Shanghai. Of course, electrochemistry is not new and has been around for quite some time. In the picture here you see a detinning plant for tin plate of 1952. As early as the beginning of the 20th century there were many electrochemical processes, but due to the fact that fossil fuels became cheaper and cheaper, electrochemistry was more and more pushed to the background. It was only used where there was no alternative. One example is the chlorine-alkali electrolysis, which is still around today. As a result of the green transformation of the chemical industry, electrochemistry is seeing a revival today, not only in industry but also in science. Electrochemistry can do such a lot. Chemical reactions can be controlled by electricity, oxidation reactions at the anode, the positive pole that is, or reduction at the cathode, the negative pole. Electrodes enforce redox reactions in electrolysis cells, and we have already seen one such example earlier on, namely the water electrolysis. There, the green energy source hydrogen is produced with green electricity. Another example is the lithium-ion battery. It is often used nowadays in cell phones and cars, and it is also an electrochemical reactor in which electrical energy can be stored. However, the focus of today's presentation is the electrodialysis. Electrical fields can cause anions and cations to migrate according to their charge to the anode, positively charged, or to the cathode, negatively charged. Salts can be split by electrodialysis. Electrodialysis is already used today to process drinking water from wastewater. Another example is the recovery of table salt from seawater. In France, electrodialysis is used very often to deacidify juices and wine. In the chemical industry, we now want to use the technology to recover raw materials from salts and as a substitute for chemicals when setting pH values. Salts are turned into raw materials again. Electrodialysis can separate salts into anions and cations. Electrolysis can build new molecules so as to generate raw materials. And this actually pays off, depending on the price of raw materials and electricity. A good example is caustic soda. We expect the price of caustic soda to rise in the years ahead. In processes of the chemical industry, we often use lyes, such as caustic soda, or acids like sulfuric acid to set the pH value. This results in processed water, for instance sodium sulfate. Electrodialysis can now convert this sodium sulfate into the raw materials caustic soda and sulfuric acid. I would now like to demonstrate by way of an example how this actually works. Sodium sulfate, an aqueous solution, now comes from our production plant. It is fed to electrodialysis. It is injected in the middle between the anion exchanger membrane and the cation exchanger membrane. Here, shown in red, is the anion exchanger membrane, whereas the cation exchanger membrane is highlighted in blue. A bipolar membrane follows downstream of the two membranes. The bipolar membrane has a very specific function. and behind this there are the two electrodes, the cathode and the anode. An electric field is created between the two electrodes. The sodium ions start to migrate towards the cathode. They pass through the blue cation exchanger membrane and reach the bipolar membrane. Due to their charge, the cations are now held back. The bipolar membrane is made up of two different membranes, namely an anion exchanger membrane and a cation exchanger membrane. Water now penetrates into the bipolar membrane and the electric field splits the water into hydroxide ions and protons. The hydroxide ions now migrate towards the anode, but are then held back by the blue cation exchanger membrane and remain in this chamber just like the sodium. And now our first raw material, caustic soda, is created. A similar process happens on the other side. The sulfate ions migrate in accordance with their charge towards the anode. They pass through the red anion exchanger membrane and also reach the bipolar membrane, where they are held back. Water again penetrates into the bipolar membrane, is split up by the electric field, and protons leave the bipolar membrane but can only migrate up to the anion exchanger membrane so that they remain in the chamber and combine with the sulfate to form sulfuric acid. And this is our second raw material, which we extract from the sodium sulfate. The process is so efficient because hundreds of membranes can be arranged in series in a single unit, as you can see here. The entire unit is called a stack, and I brought along one of them.
Hier sieht man, dass aus zwei Endplatten besteht. Die sind aus Polypropylen und pressen nun den Zellenstapel in der Mitte zusammen. Und neben den Membranen braucht man natürlich noch einen Distanzhalter, um zwischen den Membranen einen möglichst geringen Abstand zu halten. Und dafür setzen wir sogenannte Spacer ein, die nur wenige 100 Mikrometer dick sind. Das Ganze findet also in der Mitte zwischen den beiden Platten statt.
And from our Technological Research Center. It consists of two end plates which are made of polypropylene here. In sum, we recover three raw materials with the electrodialysis. On the one hand, we recover the caustic soda, on the other hand, the sulfuric acid and the water, of course, from which we have captured the salt. All three material flows can now be fed back to the production plant again. Here we see the entire process once again. We have our production plant. From the production plant we obtain the sodium sulfate, an aqueous solution, which is fed to the electrodialysis. The electrodialysis uses green electricity to convert the sodium sulfate into caustic soda, sulfuric acid and water. All three raw materials can now be fed back to the production plant again, and we have a recycling economy called circular economy. The electrodialysis provides access to raw materials by recycling, and this is a contribution to decarbonization. The technology can now be used in many of our plants so as to contribute to climate neutrality. What is more, our life cycle assessment team found that the caustic soda produced by electrodialysis has a much smaller carbon footprint, about 2/3 less actually than the caustic soda produced by the conventional process. If in addition the electrodialysis uses green electricity, this value improves again significantly. The technology can be used for different salts. Potassium sulfate is an example of a salt which can be converted by electrodialysis. Potassium sulfate can be converted by electrodialysis into caustic potash and sulfuric acid. Caustic potash is a raw material in the production of methionine. Methionine is used in livestock farming to feed animals efficiently on a sustainable basis. Another example at Evonik is sodium chloride. Electrodialysis can convert sodium chloride into caustic soda and hydrochloric acid. Caustic soda is needed for the production of sodium methoxide. Sodium methoxide is a catalyst for the production of biodiesel fuel. Another process water arising at Evonik, which provides a fascinating application for electrodialysis, is the conversion of ammonium sulfate into ammonia and sulfuric acid. Sulfuric acid is used in the polymer polyamide 12, also referred to as PA12. The polymer is used in fuel lines of cars or in large volume pipes. We are already testing the method in various processes at Evonik today. In fact, with isofurandiamine, to be more specific, isofurandiamine is a feedstock used in the production of windmills. Ammonium sulfate arises as a spin-off in the production of isofurandiamine. This can be converted by electrodialysis into ammonia gas and sulfuric acid. First trials in the Technological Research Center have been promising. Another example is the production of precipitated silica. Precipitated silica is used in energy-saving tires. When producing precipitated silica, salts, acid, and alkalis arise which can be recycled for the most part by electrodialysis. Evonik is exploring whether the technology can be used in a demonstration plant as early as next year. However, we even want to take this one step further and use the technology directly in the process. At present, we set the pH value of our material flows by adding caustic soda or sulfuric acid, depending on whether we want to raise or lower the pH value. Once the pH value has been set, the material flow is fed to the reactor, the reaction takes place, and we obtain our product and also our spin-off, sodium sulfate. The idea now is to use the electrodialysis technology directly in the process. We now pass the material flow through our electrodialysis. We have the bipolar membrane, which generates OH- ions by an electric field. We raise the pH value. The old ions are automatically captured by the anion exchanger membranes, and the material flow is fed to the reactor. The reaction takes place. We obtain our product and now do not have any spin-off anymore. There is no sodium sulfate any longer, so that we can even dispense with an entire process step. The next challenge is the scale-up of the technology and the service life of the membranes. Our biggest challenge, however, is to tailor the technology to fit our processes specifically. As yet, the technology is not readily available off the shelf. We at Evonik are working to transfer the technology to different material systems, like here in Hanau or at our demonstration facility actually, where we are working on the transfer to sodium sulfate. I'm convinced that the electrodialysis is an important lever to reduce the CO2 footprint. We have clear goals at Evonik. We want to cut the Scope 1 and Scope 2 emissions by some 25%. That is to say, from 6.3 million tons in 2021 to 4.7 million tons in 2030. We invest some 700 million euros in our facilities to emit less CO2. Electrodialysis also contributes towards these targets. We see great potential in the electrodialysis technology and expect that we can make about 20% of our processes less polluting and more efficient through the technology. For instance, by way of lower energy consumption, lower CO2 emissions, lower input of raw materials, and less environmental pollution through less salt. All of this helps us at Evonik, and it also benefits all of us as people.